Okay, hello and welcome. I'm Christoph Irwin with Positive Energy. Today we're going to be talking about insulation, its characteristics and applications. This is the introductory video to the series. We have Kimberly Llewellyn, one of our engineers at Positive Energy, is going to be speaking to you about this. You're probably going to see a little bit of overlap between the topics in the introduction here, the brief introduction, and the rest of the seminars, but that's okay. This is important stuff. It's good to hear it twice. So let's start out with a story. Why building science? Why is there such a thing as building science consulting? Why are we talking to you about insulation? This idea of science is very important. It's data driven. It's not manufacturer product claim driven. We are immersed in a culture of buying and selling. It's sort of what we all do. And sometimes the reality of a product gets lost in its sales language. And sometimes even the salespeople might not know better. So here's an example. There was a salesman, Mr. Alton King, I believe it was up in New England, and he was a salesman for a product that was known as a radiant barrier paint. Let's just stop right there. So radiant is heat energy radiating off of a surface towards anything colder. Barrier means there's a numeric definition. It has to be 0.1 or less. I mean, 1/10 of the energy or less comes off of that surface. And paint is paint, thin layer of paint. So basically this silver paint was claimed to be a radiant barrier, which it was not, because it would have to be a 0.1, and it's like a 0.25, 0.27, 0.3 as it gets dirty. So it's not a radiant barrier, it's a radiant, what we call a radiant retarder coating. But it was advertised and sold as a radiant barrier paint, and it was also claimed to be the equivalent of an R13 thermal insulation, regular trapped air thermal insulation layer. And so you can see in this picture here, he put on two layers of it, one on his attic roof deck on the inside and one on the attic floor. And so R13, he figured he had R26. His salesmen and contractors said, no, it seems like a relatively bad idea here. But he insisted. He knew better. He was the expert. And they painted his attic. And they also painted the inside of his walls and the back of his sheetrock. None of it worked. He had a very difficult cold winter. And to fix the situation, he decided to sue his builder. That's probably the most distressing part of this, but that's off topic. So it ended up going to court, and he ended up being found responsible for this because he had insisted. But the point is that it's important. We are in the trade. You, because you're watching this video, are talking to people, and you're using your knowledge to guide their decisions, and that's what we're doing. And so we need to make sure our knowledge is as accurate as it can be. And so when it comes to insulation, we need to understand what it's doing so that we can recommend it properly for the various applications. So let's just, big picture, let's talk about buildings, homes. Let's talk about the basic strategy. The basic strategy is one thing, right? You go inside and you control that environment, right? I mean, you could maybe say it's two things. You create inside with the enclosure, and then you control that environment with the mechanical systems. That's sort of what we see here, right? We have outside on the left, we have changing weather conditions. Inside, we have stable indoor weather, indoor environment. In between the two, the outdoor and the indoor, we have the control layers. And they seem to be just sitting there, but they're like the insulation, right? It seems to just sit there. But it's constantly and dynamically controlling heat flow through that. It's mediating heat flow. Moisture flow, air flow, everything's being controlled. And then you have on the other side, you have changing thing here. You want this the same. So you need some changing influence from your mechanical systems corresponding to this. So the mechanical systems and the control layers work together. And if we want them to be efficient, we're going to put in good control layers so we have predictable loads that we can trust. Once we have predictable loads, let's say good thermal insulation and a good air barrier, now we can make the mechanical system smaller, which reduces first cost and long-term costs of operation, which is a win-win, which is what we're really looking for here. We're trying to change the way that we deliver comfort to our clients. So jumping in a little bit more deeply to the control layers, right? There's four things that they're doing. We're talking about one of them today, thermal control. But they're also affecting water, rainwater, not getting in. It's actually raining outside here today. We're affecting groundwater. We don't want that to get in. We certainly don't want air to flow through our assembly. If you're going to condition the air, you need to contain the air, right? So it's important. You'll hear people say, that buildings need to breathe. Ignore that. And when you hear those people, I don't know, don't listen to them. I mean, buildings don't breathe. Buildings need to stay dry. Humans need to breathe. We need to breathe. But buildings need to dry out, which is usually what they mean when they say buildings need to breathe, because breathing, air moving through the building, can dry it out. But that's very different than we just need air in our walls. That's not true at all. So then there's vapor. There's water in vapor form in the air. We need to be mindful of how that moves through our buildings. And then today's seminar, it's very important. We're talking about thermal control, or slowing down the rate of thermal transmission through our building. And there's an important introductory thought right there. Insulation does not stop heat from moving. Insulation slows it down. So in fact, here's a little one. If you rub your hands together right now, you probably feel them heating up. You've just created increased thermal energy, but there's no heat, because heat is energy in motion. If I take, let's say, the back of this hand and I put it, now this is colder than this, so there's heat radiating from this. Now I have some heat. I have some heat moving from one to another, or I can conduct from one to another. But if the two surfaces are the same temperature, no heat flow. Same thermal energy on both. So there's a distinction, definitely, between heat, which is energy in motion, and heat energy, which is just stored thermal energy. So the building envelope is where the control layers go. The building envelope is controlling this heat, air, and moisture flow. It is supporting the building, and it is also protecting the control layers, making sure they don't get torn or damaged by UV. So that's what your walls and your roof are doing from a building science perspective. And there's more videos out there here with ICF on those subjects. So for today, this competition between information, which is proliferating and overwhelming in some sense, and understanding, which is underappreciated, is what we want to talk about, right? What we want you to do is you want to come away from this series of seminars knowing the products that are out there, the different types of insulation products, and understanding the forces that operate on them. And when it comes to the forces that operate on insulation, that force is called a temperature gradient, which basically just means a temperature hill, right? Something more of heat to less of heat, and a hill between, right? So that's what to keep in mind. When you hear gradient, just think hill, think more to less. And if you look at that three-dimensional kind of color-coded mountain on the slides here, the red is the highest part, that's where the more is, and the blue and purple is the lowest part, that's where the less is. So if that were a map of some volume of space and that was the temperature in it, you could rest assured that the heat would be flowing from the tip down to the valley, from more to less. So if you look at the picture of the house with an infrared camera, right, again, you have red being heat, the most thermal energy, blue being the least. You can see that it's radiating from that chimney around the space, out to the adjacent spaces. So temperature gradients are what causes heat to move. That's an important one. And how big are they? In a typical residential situation, we keep our buildings, let's say inside in the summer, 75 degrees. Outdoor here, our design condition is 100 degrees. That means between 100 and 75 is 25 degrees. That's the driving force. That is the driving force from outside to in. Now up in my attic, the air in those ducts could be in the upper 40s, low 50s, and the temperature in the attic is going to be 150, right? So now we have a 100-degree driving function, or thermal gradient, however you want to say it, which is a big deal, which really points to the lack of a good strategy we have when we take the coldest air in our building coming right out of our air conditioner and we put it in the hottest space in the building. And this is going to be against code soon, so that practice is going away. It only is done because it was very convenient. Low first cost dominates much of the decision making we make. So in winter we have 70 degrees inside, standard design conditions, 40 degrees temperature difference between inside and outside here in Austin, Texas. And that 40 degree, that temperature range of 40 degrees, there's another interesting thing. So one of the reasons our air conditioners work is that when they take the heat from the house, they collect it, and they make a surface outside around 150, 140, 150, 160 degrees. So again, we have this roughly a 40 degree temperature difference. So that heat outside of my air conditioner, which is over there, can radiate, can be convected out into the space because it's hotter. So we have hot moving to cold. And the main thing to take away from this insulation seminars today is that there are many products. There are many different products that you're going to have to choose from, and choosing the right one means knowing the properties of it and knowing how it's going to work when it's installed in the assembly. So this concludes the introduction. Enjoy the seminar.